Well, let's read the Hartshorne's GTM 52 algebraic geometry. We start from the second chapter. Here is the first section. So this chapter and the next chapter form the technical heart of this book. In this chapter we develop the basic theory of schemes following Grothendieck. Section 1 to 5 are fundamental. They contain a review of sheaf theory. Sheaf theory are necessary even to define a scheme. Then we give the basic definition of schemes, morphisms, and coherent sheaves. This is the language that we use for the rest of this book. And then in section 6, 7, 8, we treat some topics which would have been done in the language of varieties, I mean classical variety, but which are already more convenient to discuss using scheme. More convenient to discuss. For example, the notion of character divisor and of an invertible sheaf, which belong to the new language, greatly clarified discussion of wave divisor and linear system. Which belong to the old language. So wave divisor linear system, this is old language, but if you use language of scheme, so on, you can use character divisor things, as you will see. This will actually be described by sheaf. Actually, this will corresponds to a line bond. So locally free sheaf will rank 1. We will see later in section 8 the systematic use of non-closed scheme points gives much more flexibility in the discussion of sheaves differential and non-singular variety, improving the treatment in the first chapter. In section 9 we give the definition of formal group which did not have an analog in the theory. In the theory of variety, it was invented by Grothendieck as an analog, as a good way in dealing with Zariski's theory of homomorphic function, which Zariski regarded as an analog in abstract algebraic geometry of homomorphic functions and neighborhoods of a subvariety in the class. We start. The concept of sheaf provides a systematic way of keeping track of local algebraic data on a topological space. We start from topological space X. What are the local data? And how do you keep track of it? For example, the regular function or open subset of a variety. As introduced in the first chapter, form a sheaf. So I mean, you will say sheaf. You can define many ways sheaf, which is just a functor from the category of open subsets of the topological space to the category of abelian groups, for example, or rings or modules, something like that. Anytime you want to study some local property of this topological space, for example, you want to say the regular functions as mentioned here, so you want to say on any small open, what are the regular functions on it? You just apply your sheaf to this open set, and it gives you the regular function as all the regular functions as a group on this open set. This is the sheaf of regular function. Whenever you want to study the local property, you can manage to define a sheaf of that thing, and the knowledge developed later for sheaves give you techniques to study those properties in more detail. So sheaves are essential in the study of schemes. In fact, you cannot even define scheme without using sheaves. So scheme is you can say a generalization of the idea of a geometry object. Before, when we say geometry object, actually we mean in some sense it's set theoretically. I mean, when you define topological space, you care about what are the points of topological space, what are the open, what are the closed. It's set theoretically in some sense. But we saw some phenomenon which shows us that although object A and B are set theoretically the same, but if they are arising from some zeros, a polynomial, for example, we say variety, sometimes very different polynomial give you the same set theoretically geometric object, which we are not satisfied to say okay they are the same. So our thinking is that we want to be more precise, more detail of what we are talking about, not only set theoretically, but can also distinguish the algebraic polynomials, the algebraic structures that associate to them. For example, if you say x squared equals -1, if you consider it in this coordinate ring, this will give you just empty. You see the problem here. Usually, as we saw in Hartshorne in the first chapter at the beginning, we are talking about the algebraic variety or algebraically closed field. In that case, we have correspondence between the prime ideals and the reducible variety, subvariety. In situation like this, you see the polynomial corresponds to the zero set inside this affine space. This affine space is endowed with a risky topology, and the ideal corresponds to the zero elements of all the elements of it. So you say for this x squared -1, if my key is R, this one-dimensional case, Their element is empathy. And same thing happens for identity element. While if you look at their coordinate ring, x over x, I, x over f. In our case is rx over x squared minus 1. This is rx over the prime ideal over the whole ring. It's isomorphic to the trivial ring. But you see, this is not isomorphic to the trivial ring. This is, in algebraic sense, this is well defined. This is just an R algebra. But you see, this very different R algebra give rise to the same theoretically geometric object, which is not reasonable. Of course, you can say, well, let's just work over algebraically closed. Even though that is not good enough. For example, this one and this one, they are very different in algebraic sense. This is not reduced to this. But you see, that theoretically they are the same, just a zero element itself. So there are some problems with the classical algebraic variety. Theoretical point of view is not subtle enough, it's not delicate enough to remind you of the algebraic structure. We can be more precise of the classical theory. Let's recall corollary 1.4, which tells us there is a one-to-one inclusion reversing correspondence between algebraic set in AN where, let's recall, I put it a subset Y of AN is an algebraic set. If they reduce a subset, T contained in A such that while A is coordinate to green, such that Y is 0 set of this. Okay, it's just subset here. Okay. Between algebraic sets, A and radical ideals. So those ideals equal to the radical. It's given by have algebraic set descending to your ideal. Now you have radical ideal descending to its 0 set. Furthermore, the algebraic set is reducible. If only if its ideal is prime ideal. Remark. So we see the correspondence is not between any algebraic structure and geometric objects. It's only between radical ideals and algebraic sets, which is, as we said, not good enough. Well, but we should know this is in some sense good in its own sense. In what sense? This can at least get rid of the problem that x squared as ideal corresponds to the same point as x inside, let's say A. Why? Because this is x, it's not x squared. So to be radical, actually get rid of those cases, this non-reduced ideal. I mean, get rid of this. So the radical ideal is those elements whose reason to some power lies in it. Okay, but still it's not good enough, as we said. For example, x squared, when surely this is in the algebraically closed case. As we said, if you are in Rx, this is a prime ideal. Okay. Fact. Prime ideals are all radical. So this is radical. It's prime ideal. But it doesn't correspond to a irreducible subset. It corresponds to empathy. Okay? So you see, we do rely on case algebraically closed. These are some weak of the old point. So let's go on to say how our scheme language works. Let X be a topological space. A pre-sheaf of abelian groups consists of the data. First, for any open W, it associates an abelian group. Second, for every inclusion of open, it gives a morphism of abelian groups. Subject to the condition, mapping empathy to 0, mapping identity to identity. And compatible with composition. This is just in the language category, as here is said. For any topological spaces, we define category. The objects are open subset. The only morphism are inclusion. Only morphism inclusion. Hence, the whole is empathy if they are not containing each other. And if with containing U is just one element, inclusion, morphism. So now the pre-sheaf is just a contravariant functor from the category of open subsets of X to the category of abelian groups. We define a pre-sheaf of rings, a pre-sheaf of sets, a pre-sheaf with values in any fixed category, say, by replacing the words abelian groups in the definition by a ring, a set, or object of set respectively. We will stick to the case of abelian groups in this section. So our sheaf will be pre-sheaf of abelian groups. And let the reader make the necessary modification for the case of rings, necessities, etc. As a matter of terminology, if F is a pre-sheaf on X, we refer to Fu as the sections of the pre-sheaf F or the open set U. We just call the elements inside this. So this is abelian group. Okay. We call the elements of its sections. Sometimes we use this to denote this group. We call the map restriction maps. At least sometimes write this. It's just notation. A sheaf, roughly speaking, is a pre-sheaf whose sections are determined by local data. So you want to know how is this contravariant functor from the category open sets of X to the category of abelian groups work. To know this functor, you have to tell me on each object of your starting category. This is open U. What is a group FU? See the sections on U. To be a sheaf is saying that those elements of this group FU is completely determined by local data, which means if you can use some smaller open subsets to cover U, and you know the sections on those covered, then you know the U. You can glue them together. Precisely, it's written like this. The pre-sheaf F on topological space X is a sheaf. It satisfies if it satisfies the following supplementary condition. First is, if you have open covering and section on a big open U, so U is the union of those VI, and by the definition of our pre-sheaf, since each VI is containing U by inclusion, so we have a morphism. What do you call it? If V is containing U, then we write row UV. So we have row UVI from FU to FVI, which we also denote by just this. It says if this morphism mapping some element of this subling group on its sub-open VI to 0, to this group homomorphism map S to 0 for any I, then S must be 0 itself. And if U is open, if VI is an open cover of U, and if we have elements in those groups which has a property that when you map in those elements to the group FVI intersect with VG, they coincide for any I and G, then you can glue them all together to element of FU. Okay, so sometimes we call this glue condition. This is called uniqueness. According to our definition, a sheaf is a pre-sheaf satisfying certain extra condition. This is equivalent to the definition found in some other books. Well, when we have time, we will explain this. We call this scheme 001 to explain this equivalence definition of sheaf. Actually, Goldman has another description. Let's say some example. First, let X be a variety over the field small k. For each open U inside X, let OU be the range of regular functions from U to K, and for each V contained in U, let this row U just be the restriction map. So for regular function, you know what it means to restrict on V. Okay? By the restriction map, then O is a sheaf of rings. It is clear that it is a pre-sheaf of rings to verify the condition thread for. We just know that the condition which is 0 locally is 0. So regular function which is 0 locally is 0. And function which is regular locally is regular. This is an easy case because first of all, your sections are all functions. You see, your sections are all functions. So for functions, the uniqueness is obvious. If you are a function, when you restrict it to a covering, you're mapping to 0, so yourself is 0 by definition. And by definition of regular function, it is that for a point. Okay, first let's say, recall that for Hartshorne, variety always means irreducible. Okay, so for any point P, a function is regular on the point P if there exists open cover of P, open set containing P such that F defined on this U is the form G or H for GH in the coordinate is in the p-algebra polynomial, real polynomial, and each restrict on U is never zero. There is no 0 points. That's the definition of regular at a point, and regular on X if it's regular on every point. So you see, if you have an open covering, let's say for example UI, UG, UI, U2. For U1 you have a regular function F1, here you have a regular function F2. Then I am going to define a function defined from U1, U2, U2. Okay. For the elements in U1 I define it by F1. For elements in U2 I define it by F2. Then this is a function on the intersection. Since they coincide, okay, it's well defined. It's well defined, this function. And is it regular? So for any point, can you find an open subset containing this point, such that this function restricted at this small open is the form of G or H? Yes, that's the definition. Your point, if your point is falling into U1, then you take open set. By definition, a regular function F1, it should be of the form. If you are pointing U2, then you take F2. If you are pointing U1 intersection U2, you take whatever you want, F1 or F2. And the point is, it is well defined as we first checked. Okay, because it is just a function, nothing to prove. Okay. In the same way, one can define the shape of continuous real-valued functions. Functions are easy to deal with. Only topological space, or the shape of differential functions on differential manifold, or the shape of holomorphic functions, complex manifold, whatsoever. The X topological space and A abelian group will define the constant shape on X determined by an abelian group A as follows, given A the discrete topology. Give A a discrete topology. Give A a discrete topology. So it's topological. It's an abelian group with discrete topology. Surely I didn't say it's topological group, I just say it is abelian group. So there are elements, and I give it discrete topology, making it a topological space. Okay, so for any open set UX, define this. This is the shape we're going to define to be the group of all continuous maps of U into A. This is with discrete topology. So the continuous maps means the inverse image of any point of A is open. Okay. Then with the Euro restriction map, we obtain a shape. Note that for every connected open set of U is isomorphic to A with the name constant shape. So you only to have to remember the definition is like this. But how is it defined is like about, but the important thing is just any open connected open is defined to be A. Okay. This is very reasonable. For example, just saying that what is a continuous function? Like we must map the whole space to a single point A. Otherwise, it's connected, Otherwise, if I map into 2 points different, so with the discrete topology, they're both open. The inverse image open. If inside your connected component you map into some different point, surely they cannot. The inverse image cannot contain each other. So any 2 points the inverse image cannot intersect each other. That's a problem. There should be some very clever proof, but for example, let's just say the fluid. Let's say if our U is, say image has 2 targets, has 2 elements different. So first take the inverse image with this point, so this is open. So all the remaining one have to be mapped to this point. But this is closed. But the inverse image of this is all of this. So inside this topology of U as topology of space, those mapping to this point is both closed and open, which tells you it must be empty of the whole space, okay? Which kind of contradiction, okay? But this is a stupid proof and just fail it, okay? If U is an open set whose connected components are open, which is always true on locally connected topology of space. So for locally connected topology of space, it means for any point you can always find a small open which is connected. If U is open set whose connected components are open, then it's just direct product of copies of A and 1 for each connected component with U. So if U is like this with several connected components, each of them, the continuous function can map each of them to a point, same or not, okay? Definition: F is a pre-sheaf on X, and if P is a point of X, then we define the stock of this sheaf at this point to be the direct limit of the group. So this is a system of groups for open sets U containing P with a restriction map. So this is a direct limit with a transition map. For example, U is inside V, so we map to U through V. Yes, that's a transition morphism, and they all map to direct limit. Okay, this is stock. That's an element of FP. Since this is direct limit, you can realize it for this filtered inductive system. You can realize that as each one of them is a Abelian group. The direct sum of those FP cushioned by the relation, which is U is an open neighborhood. It's represented. Elements here are equivalence classes. Okay. Here's any U and V which contain P. Okay. Sorry. Any U and V contain P. On point P, you have all opens containing it. Sorry, it's not nice to write this. Write disjoint union. Okay, this is obvious. So for each open U and any regular function f on it, you take its equivalence class is an element in this FP. So we used to say that two elements of disjoint union in the same equivalence class if there exists some smaller w containing their intersection such that these two sections are the same. Okay, so we may speak of elements of the stock FP as germs of sections of F at the point P. In the case of right X and its shape of regular function O, the stock OP. In the case of a right X and its shape of regular function, if we define by O the stock OP, at point P is just a local ring of P on X. Let's recall what is written there. So definition to y, and y will write denote y o y, the ring of all regular functions on y. Phi is a point of y. Define the local ring of P on y. Denoted by or simply by P. To be the ring of germs. Regular functions on y. Near P. In other words, an element of OP is a pair. Where U is an open Y. Containing P. And F is regular function. And U, where we identify two pairs if, that's the same way we defined. So obviously for the sheaf of regular functions, the stock is just the local ring of P. The same thing, okay? For the sheaf of regular function, so you see we redefine the local ring of regular function by the stock of a sheaf of regular function. Okay. The morphism, we define morphism pre-sheaf is just natural transformation factor. So sending any morphism in the category to morphism in labeling groups, and for any given object, there is morphism in the category labeling groups, making the diagram commutes. Okay. If they are sheaves, then we use the same definition. And morphism is a isomorphism is a morphism with two-sided idea. Note that morphism pre-sheaf induce morphism on the stocks. Okay. So suppose taking the open neighborhoods of P, then all of them map into FP. Now those map into G of P, and thence all those F through those morphisms map into JP and making it commutative. So by the universal property of this direct limit, there must be a morphism. Mapping to this, okay? You run this, so there exists something such that there are still morphisms making the diagram commutes for any morphism in the index set M to N. In this case is by the commutative of this, we know this map and this map for the morphism we include U commute with this. So for this index set open subsets, any inclusion corresponds to morphism in the index set gives rise to morphism of the ring group, making the commute diagram commutes. So by the universal property, this has the inductive limit of those ring groups must map into this GP. Okay. proposition that phi be a morphism of sheaves on top of your space X, then phi is isomorphism if and only if the induced map on the stock is isomorphism. This is nice, but it's not difficult. You should do it. It's nice. For morphism pre-shift given, we define pre-shift kernel, pre-shift co-kernel, pre-shift image in the obvious way. Just define it on each open to be the opening group. Obviously, as it should be. Note that if this morphism sheaves, then the pre-shift kernel is actually a sheaf. But the pre-shift co-kernel and pre-shift image, not in general, not sheaves. This leads us to the notion of sheaf associated with pre-shift. That is called sheafification. Okay. Given pre-shift F, there is a sheaf F plus and a morphism with the property that for any sheaf and any morphism there is a unique morphism. So this is a universal property. Actually, this is telling us that forget factor and sheafification are joint pairs. I mean, this is in the category of sheaf. Forget, how do I say forget? Just forget, okay? Forget the sheaf structure, become a pre-sheaf. Yes, precisely. Give a pre-sheaf F, there is a sheaf F plus the morphism, so with the property that for any sheaf G and any morphism of sheaf, there is a unique morphism making this diagram clear. So this morphism phi is actually pre-sheaf has pre-sheaf and is in bijection with all these morphism sheaf after sheafification. The joint pair or the joint functor is just, this is the definition, this is just bijection and set. Okay, this is what this proposition will tell us. And a subsheaf of a sheaf is obviously for any open give you a subgroup. Okay, and the restriction map is the map of the group we restrict our subgroup. It follows that for endpoint P the stock is also a subgroup. If phi is a morphism of sheaf, we can define the kernel of phi to be the pre-sheaf kernel of phi, which is also a sheaf. So kernel is an example of subsheaf. Okay, we say a sheaf, a morphism of sheaf is injective if the kernel just defined as a subsheaf is 0. This is equivalent to say for each open U this is injective, but for surjective it's different. We can define the image of a morphism, but it's just a pre-sheaf, not in general a sheaf. We see morphism of shape is surjective if the image of phi as a subshape of G is G itself. Now we define a shift sequence of shape is exact if kernel equals image. And we can also define quotient shift. As I mentioned just now, phi is surjective if and only if the maps on stocks are surjective. But it's not true, section wise is surjective. We can define some operations on shapes associated with a continuous map from topological space to another. So if we start from a continuous map of topological space, then for any shape on X, we can define some shape on Y, called direct image shape, by this way, obvious way. For any open of Y, we took its inverse image. And start from a shape on Y, we can define the inverse image shape. To be the shape associated to the pre-shape. So for any open U in X, we define for any open U in X, we first take an open containing FU. Well, if FU is already open, then it's easy, you just define it using the shift G acting on FU. But the problem is that F is not an open more homomorphism in general. It doesn't send open to open, although its inverse sends open to open because it's continuous. So the way is to take all the open containing FU to the direct limit. Call this direct image, call this inverse image. Yes, F star is just factor from the category of shapes on X to category of shapes on Y. F inverse is a factor from category of Y to category of shapes on X. If Z is a subset of X regarded as topological subgroup subspace with the induced topology. If Z in X is the inclusion map. And if F is a shape on X, we call this so the pre-image. Sorry, the inverse image. Call it the restriction of F to Z. So F evaluate on any open of Z. It's by definition. F evaluate on U by injection into X and taking the inductive limit. And all the open we contain U. Denote this by restriction. Note that the stock of this inverse image sheaf. At any point P of Z is just Fp itself. It's the same. Let's see, how can we say this more clearly? For example, so you have X, you have Z. Take any point of Z. Where in the case Z is inclusion map, no matter close or open, just inclusion map. If you are inclusion, okay, nice. Just inclusion. So this is the definition. Let's say, what's its stock? It's for any point of Z. The stock is the direct limit of open containing P inside Z. Yes, and this is first open of Z contain P, and then open of X contain U. So let's see, what is this? This is the open of X that contains an open of Z that contains P, which means that for open of X such that contains open of P that contains P, which is exactly the open of X contain P. Okay. Of course, if you want to be more precise and rigorous, here you should use universal property to construct a morphism from here and there. But the idea is like this. Any open of X containing P will intersect with Z. It becomes an open containing P in Z. Any open of Z containing P comes from an open of X. So it's okay.